I'm now going to introduce what a graphical model is, which you can think of as a data structure that's going to enable us to store probability distributions efficiently and to also solve various inference tasks efficiently on a computer. I'm going to build up to the general definition for what a graphical model is through some examples. Let's get started with a simple example where we have two random variables x1 and x2 where we know that they're independent. This of course means that the joint probability distribution of x1 and x2 given by p of x1 and x2 evaluated at little x1 little x2 is going to be equal to the product of the marginals, which is p of x1 of little x1 times p of x2 of little x2. Okay? And of course when we write an equation like this, we mean that this holds for all little x1 and all little x2. Oftentimes as a shorthand we will just write px1 x2 equals px1 px2 without writing the little x's. What this means is that if we want the joint distribution for x1 and x2, we can get away with storing just the probability tables for x1 by itself and x2 by itself. And so something to note is that this thing here depends only on random variable x1, and this thing here depends only on random variable x2. I'm going to introduce some notation now that might seem unmotivated, but we'll see why we're doing this shortly. This thing I'm going to also call phi1, and this thing I'm going to call phi2. So for example, phi1 of x1 and phi2 of x2. The idea is that each of the phis will just depend on one of the random variables. And later on we'll see examples of where the phis are not just the marginal distributions. Alright, so the next thing is looking at how to actually draw a graphical representation here. And what we're going to do is we're going to write x1, so random variable x1, and we're going to draw a circle around it, and then we're going to write random variable x2 and draw a circle around it. And so these circles represent random variables, and note that the x1 and x2 circles are isolated. There isn't a line connecting these two because they're independent. Here we see our first graphical model of the course. So x1 and x2 shown in this graphical depiction, and we also provide the tables phi1 and phi2. Okay, so this here is our first graphical model. So now let's move on to our second example. Suppose we still had random variables x1 and x2, but we don't know whether they're independent or not. Without making any additional assumptions on x1 and x2 to reason about how they relate, we're just going to have to look at the full joint probability table px1 x2 of little x1 little x2. And so here this thing of course depends on random variables x1 and x2, and we're now going to introduce yet another piece of notation where we call this psi 1 2 of little x1 little x2. We'll use psi to represent tables that depend on two random variables. So the graphical model here is going to look like, first we have x1, which we put into a circle, and then we have x2, which we put into a circle, and then we have a line that connects them, and the line is here because we have a factor psi that depends on x1 and x2. So here the graphical model is given by this picture right here, and we supply a table psi 1 2. And here I will say that the graphical model used for representing this joint probability table is actually not unique, in the sense that we can actually store a graphical model for this distribution in a different way. And to make that clear, I'm going to show you a different graphical model that actually stores the same distribution. And what I'm going to use is, if you remember, the product rule holds regardless of whether x1 and x2 are independent. So we have p of x1 of little x1 times p of x2 given x1 of little x2 given little x1. Of course, this thing here is true for all little x1 and little x2 such that the probability of little x1 is greater than 0. We've mentioned before, if this thing is 0, this whole thing is 0. Alright, so now note that I have a piece here that depends only on x1, and a piece here that depends on random variables x1 and x2. Here, this thing I can call phi1 of x1 And this thing I can call psi1, 2 of x1, x2. Okay? And this psi is different from this psi, okay? I'm using different colors to mean that they're different things rather than writing, for example, prime. So a different way is, instead of providing this table psi1, 2 that's in red, I can have phi1 and psi1, 2 that are in orange. Okay? So I can instead supply these two tables plus this graph, and that's a different way to represent the same distribution. Of course, if you remember the product rule, you know that, well, we can actually also write this as p of x2 of little x2 times p of x1 given x2, little x1 given little x2. Okay, and of course here you can see, well, this thing I can write as phi2 of little x2, and this thing I can write as psi1, 2 of little x1, little x2. And so a third way to represent the same distribution as a graphical model is to supply these tables in blue, phi2, psi1, 2. And this is just to emphasize that for a given distribution, how we represent the graphical model is actually not going to be unique. However, one thing that is unique across these three different ways is that the graph stays the same. Every time we have x1 in a circle and x2 in a circle, and we have a line between them. And we have a line between them precisely because in all three of these different ways of representing the same distribution, there's a factor that depends on both x1 and x2. Okay, so let's move on to a third example. Now we're going to look at if we had three random variables, x1, x2, and x3, where I'm going to make a very big structural assumption. I'm going to assume that the joint probability table of x1, x2, and x3 is going to factorize as p of x1 times p of x2 given x1 times p of x3 given x2. So note that in general, for a distribution over three random variables x1, x2, and x3, this factorization is not going to be true. And one way to see that is as follows. We can always write out the product rule, which holds regardless of any structural assumptions on the distribution. So the product rule says that p of x1, x2, x3, I can write this as p of x1 times p of x2 given x1, and then times p of x3 given both x1 and x2. And so this is true in general. By comparing these two equations, because they're both representing the joint probability table, we see that this structural assumption says that this thing is equal to this thing down here. Okay? The probability of x3 given x1 and x2 is the same thing as the probability of x3 given x2, meaning that x1 doesn't tell me anything new about x3 given that I already knew x2. This thing here is stating a conditional independence, that x3 is conditionally independent of x1 given x2. So this assumption here on the joint distribution of x1, x2, and x3 can be stated as a conditional independence. Now let's look at what the graphical model is. So first off, we have a piece that only depends on x1. We're going to call this phi1. And then we have a piece that depends on x2 and x1. So this will be psi1, 2. And then here we have a piece that depends on x2 and x3. So psi2, 3. And so the graphical model is going to look like, first we have random variable x1, which we put into a circle, x2 also put into a circle, and then x3 also put into a circle. And then we look at the different factors and we see, there's a factor that depends on x1 and x2. So that means I put a line between x1 and x2. And then I see, there's another factor that depends on x2 and x3. So I put a line that connects x2 and x3. For this graphical model, I can specify this graph, and I provide the tables phi1, psi1, 2, and psi2, 3. And so this kind of graphical model where we have a line is actually what's called a Markov chain. And the notation we'll use to say that x1, x2, and x3 form this line is that we're going to draw these arrows, okay? So x1, left right arrow, x2, left right arrow, x3, okay? So that's just some notation that we'll sometimes use. Now we're ready to state the general case. We saw that we have circles, and we also have lines that connect the circles. The technical name for circles are what are called nodes or vertices. And the technical name for the lines we were drawing are called edges. And so as we saw, each node represents a random variable. And each edge appeared because of there being a factor in the joint probability distribution that depended on two random variables. So you can think of this as each edge represents a possible dependence between two random variables. So in particular, if there is an edge between xi and xj, then this means that there is a factor in the joint probability table that depends on xi and xj. And of course, we saw that this factor would be called psi ij. Okay, and up here, each node could possibly have a function associated with it, phi I. Okay, so these phi i's and psi ij's are tables. 1D tables for the phi i's and 2D tables for the psi ij's. Okay, an important thing to note is that more edges implies that the graphical model can encode more possible distributions. So importantly, note that having an edge like psi ij, you can still actually encode the case when xi and xj are independent. So to make that concrete, going back to our example of just x1 and x2, note that psi 1, 2 here can actually have x1 and x2 be independent. Okay, so somehow having this edge does not mean that, oh, x1 and x2 can't be independent. Having this edge means that we don't know whether x1 and x2 are independent, and in fact, having this edge, we can encode x1 and x2 being independent. However, in the first case we saw of this graphical model, where x1 and x2 are independent, this graphical model has no way of encoding a joint probability distribution for x1 and x2, where x1 and x2 actually are dependent. Okay? So, again, importantly, more edges means that we can encode more possible probability distributions. Okay? And of course, having more edges means that you're going to have to store more tables. So, in this class, we're going to focus on graphical models where there are no loops. Okay? So, for example, we don't have a line going like this. Okay, that would create a loop. Okay, so no such lines. And you can think of it as, if you have those lines, then you would have circular dependencies, which we're not going to deal with. Okay? And now I'm going to write out what a graphical model is mathematically. So a graphical model has a graph associated, so we were showing those pictures of circles and lines. Those are graphs. A graph mathematically will write as G is equal to V, the set of vertices, comma, E, the set of edges. So when we had just x1 and x2, then the graph here would be given by the set of vertices here is just 1, 2, and the set of edges is the empty set because there are no edges. And when we had x1 and x2, where there was a line between them, then the graph is given by, well, we still have the vertices 1 and 2, and we have a set of edges, and there's only one edge, which is the edge from 1 to 2. And so edges will write of the form I, j, where edge ij and ji are the same thing. Okay, and we're not going to separately write in the edge set 1, 2 and 2, 1. And as a third example, of course, we had the Markov chain, x1, x2, x3, and this thing, the graph, is given by vertices 1, 2, 3, with edges 1, 2, and 2, 3. So we have this graph where V is going to be from 1, 2, up to n, where we have, in general, x1, x2, up to xn as the random variables. And again, the set of edges, no loops are allowed. So as a formula, we'll write that the joint probability table for random variables x1 up to xn, of little x1 up to little xn, this thing is given by the following factorization. We're going to have, for each I in the set of vertices, we're going to have phi I of xi, and then for each edge ij in the set of edges, we're going to have psi ij of xi xj. Finally, we're going to have this normalization factor here, z. This constant z just ensures that this probability table actually sums to 1. So given a graph G, V, and E, and the tables VI's and psi ij's, we immediately get what the joint probability table should be by this formula. And so these, the phi's, are called singleton potential functions, which we'll also just call singleton potentials. And the psi ij's are what are called pairwise potential functions, or just pairwise potentials. And importantly, these potential tables here have to have non-negative entries, but they don't have to sum to 1, okay? And we'll see a lot of examples where they don't sum to 1, and the key thing here is that the reason why this whole thing is still a valid probability distribution is because of z, okay? Just by specifying what the potential tables are, we don't have to specify what z is, because z is going to be the normalization constant that makes sure that this whole probability table sums to 1. So this thing here is what's called an undirected graphical model. It's called undirected because the edges don't have a sense of direction, okay? We don't have like an arrow where it matters whether you're going from 1 to 2 or 2 to 1, okay? So no sense of direction, and this is technically what's called an undirected pairwise graphical model because we're at most looking at 2 random variables at a time with the potentials. And also I'll say that oftentimes people call this a Markov random field. So this is just another name for undirected graphical models. But in this class, we are just going to refer to this as a graphical model. So something to note is that earlier, some examples we saw, not every random variable had a phi I. And mathematically that's okay, because for a random variable, if you don't actually have a singleton potential, you can think of it as we just have phi I of xi equal to 1 for all possible xi. And then that particular term would just always be 1, and everything is still fine. We still have this factorization. Okay? So we'll be seeing a lot of examples of graphical models, and very soon we'll also be looking at how to incorporate observations and also how to solve various inference tasks efficiently using this graphical model representation.